use is here. Here appear the download of MedGraph. Okay, so we have here this file that is a tar file. So we need to extract the content of this file, and this is all. Now MatGraph is installed in our system. It's very simple. So we open the folder and we can find different folders and files. For me, one of the most important folder is the models folders, because we have here models, and for example we have as default this standard model SM. This standard model is a UFO file. UFO file, remember, are Python files that MatGraph reads to do the calculations. So each one of these Python files, for example, parameters, we can display. We have in a specific syntax the information about in the case of parameters, the information about the parameters that the standard model use. For example, we have the Fermi constant. We have that is external parameter. Remember, external parameters are numbers. Internal parameters are parameters that depends on another parameters. So Fermi constant has that value. All the values here that has units are in GeV units. So we have the strong coupling constant. We have the mass of the particles. We have the mass of the charm of the bottom, and we have all the, for example, the width of the Z boson is that value. So important thing that is mandatory to comment here is that we don't need to modify that files. That files were implemented using programs like find rules. Find rules do that work automatically. Find rules generate all that Python files, so we don't need to modify that files. This is important. So we have here the standard model and another for example, we can, this is the files. Okay, this is the most important file folder that we find in MatGraph, and continues with the lecture. We have here the second part of the lecture, that are the main MatGraph commands to generate events, to calculate the cross section and decay widths using the interface. For example, the first command is in red. All the commands that appear here are in red, and this is the command to initialize MatGraph. So to do that, we need to enter to the main folder of MatGraph and click with the right button and open the terminal. That terminal is inside of the main folder of MatGraph, and inside of the terminal we are going to write that command. That is the same command that appeared on the slide. If we do that, MatGraph appears. MatGraph is open, and this is the interface of MatGraph. We have different information here. We have a presentation. We can do it a tutorial. If we type tutorial, we can learn about some properties and some features of MatGraph, and we can see that MatGraph for default load the SM model. SM is the same model that appear inside of the models folders. MatGraph charged that for default that model, but we are going to see that we can change for another model with another command. And we have here the information of particles with a multiparticle. Multiparticle don't mean that the particle is composed by another particle. It's only a feature that MATLAB use to inform that that variable, in the case p, that is the proton, contains that set of another particles. Okay. For example, the lepton. Lepton contain electron and muon, but don't contain the tau charged lepton. We have here the neutrinos, electron, muon, and tau neutrino. We have when we have that symbol that appear in the right hand of the field, that means that this is the antiparticle of the particle. So we can, for example, another important things that we can install different complementary package to do the simulations. For example, we can install Delphis, we can install X-root analysis, we can install LHAPDF6, we can install media analysis 4 and media analysis 5. We can install Pythia, that is very important. And the most important complementary package are I mentioned there. Delphis, X-root analysis, Pythia, media analysis 5, and LHPDF6. My work here is don't install that package because can take a lot of time. So I have my MedGraph installed in another folder, and I have already that installation. So this is only example. For example, if you do install Pythia 8, you install Pythia 8 obviously. For that, for some of that package, alternative package, you need to install a root from CERN. So I have a tutorial that I can send to install root, and you can install the LFS, X-root analysis, Pythia, media analysis 5, and LHPDF6. A comment here is necessary to LHPDF6. Why? If you send LHAPDF6 okay. If you search, you have a site that has all the PDF sets that the nuclear physicist experiment find. There are a set of data that represent the probability that you find a specific quark or a specific gluon, I mean partons, interact with another partons. And if you remember the lecture number 3, the principal objective of MedGraph is solve the evil equation, that is the quantum chromodynamics master formula. So the parton distribution functions are a set of data that you need to download from this site. You know, exists a lot of data that each one represent different interactions. So if you do some simulation, you need to take in account what is the LHPDF characteristics that you need to do the correct simulation. So continue with the lecture. You use install word, and you put the number of the package that you need to install. Other command, you can inside of MatGraph, if you are using, for example, in this case for the full standard model, you can display the particles that contain the standard model implement inside of that folder SM that are inside of the model folder. So we have here, for example, the W plus, W minus, that is the W boson. We have the electron and antineutrino electron. We have the muons and tau neutrinos. We have the quarks. We have the charged leptons. We have the photon that is represented by the A letter, and we have the Z boson, the gluons, and the Higgs. So we have that particles that are contained inside of SM model. Okay, we can display again multi-particles that are variables that we define to contain another particles. For example, we can modify that the electron and muon that are contained in L minus. The form that we can do it, that is defined L minus is equal to minus that contain electron and muon and the minus, for example. Now, if you display again multi-particles, you see that you have now electron, muon, tau. Remember, that don't means that the lepton contain only electron, muon, taus, because we can do it, for example, the L minus and Z boson, for example. So if I display the multi-particles again, we have the Z boson appear here. That okay. So that means that that particle L minus is not a new particle. It's only a variable that contains that particles, but not represent a physical particle. Okay. So we can use exit to exit from MatGraph, and again we can start MatGraph with the same command. Okay, the variables, now we have the variables for the fall again. Another command that we can display, for example, model list. The model list are the model that we can download automatically. We have a set of models, and in the first lines we have the models that we have in the models folder. Okay, and we have another models that we can install, the 2HIGW model, and another model that we can download and improve using the commands that we are going to show. So another commands important is, for example, inside of the standard model we can display interactions. So we have here all all the interactions that we have inside of the standard model. We have the interactions between 4 Higgs. We have the interactions between 3 and 4 gluons. We have the interactions, for example, between the Z boson and 2 pairs of muons. So with that command we can show the interactions that were implemented inside of the SM model. This is another important command. I explained that command and that command. We now this is the basic commands, and now we need to generate events. For example, we use the word generate, and we need to physical process that is available inside of the model that we consider, in this case the standard model. So we use, for example, generate positron electron positron electron. With that command appear that message, and we can see the diagrams, display diagrams. With that command we can see the diagrams of that process. We have the process between the photon, electron positron produce a photon, and then produce a pairs of electron positron. We have that process, electron positron produce a Z boson and produce again an electron positron pair. And we have the T channel that produce again an electron positron produce in the T channel a photon and a Z boson. You can note here that we don't have the Higgs boson. Higgs boson appear inside of the standard model for that type of interactions. So to appear that model that contains the interactions between the electrons and muons, for example, we need to open again fine rules models. If you compile that model, standard model, for example, here remember you need to define the folder of that contain the main folder of fine rules choose. So, and with that command we can load fine rules. Okay, these were present in another lecture, and here we need to inform the folder that contains the SM model that for default is the same. So we charge here the SM model, and we need to inform the fr that file fr that contain all the standard model. Okay, all the standard model. So we charge the standard model, and we need to be here in output and interface and search the UFO files. UFO files are the Python files that MetGraph use. So we execute that command and produce starting the Feynman rules calculus and generate all the Python files that MetGraph needs to do simulations. So we wait, and with appear the done word means that the calculation were finished. Here done. After that appear a new folder that contain the Python files. This is the function of find rules. Okay, so we can change the name SM with Higgs, for example. Now, what is the following step? We need to send that model to the folder that contain the models, that is this folder, and you copy that model. Okay, and inside of MedGraph you charge again MedGraph, and for charge for load another model you put import model, in that case the name of the model, sm with Higgs. And if you do that, you can generate, for example, generate E plus, E minus going to E plus, E minus, and display diagrams. Now appear again the same models, but appear the interactions with Higgs. Okay, so that command is important. Import model, because is the same, is the form that you need to do physics beyond the standard model, because you use find rules, implement a new model, generate the Python files, the UFO, Universal Feynman Rules output, that means UFO, and you copy the folder that result of the calculation via find rules, and you send that folder inside of the models folder that appear inside of MedGraph. So we have here the standard model using the Higgs boson. We can close that. We can close Mathematica and continues with the lecture 4. So we can generate, for example, the second process. We can generate electron positron going to electron positron again. As I say, we have 6 diagrams, and we can show, for example, display process. We have only one process, that is electron positron going to electron positron. That is only one process, and we can generate the events, generate the files that MATLAB need to solve that integral. Okay, that command is output, and you can use any name that for the calculation. For example, a model example. So MATLAB do the calculations to generate that events, and here in the main folder appear that folder. Inside of that folder we find, for example, the process information. We have all the Feynman diagrams, and we need to do the calculation for that. To do the calculation, we need inside of the model example, that was the folder that I created. We have different folders. The main folder here is cards. Why? Because we have 2 files that are very important, that is run card and parameter card. For example, in parameter card you can modify the informations of particles. You can modify the mass of the particles, the width of the particles, and some another parameters. If we consider, for example, another model that is beyond the standard model, I need to open param card and modify, for example, the mass of a new Z prime that appear in that model. So this is important to understand that file. And run card, for example, in run card you has the information about the collider. Okay, we have, for example, the number of events. The number of events is important because are all the random numbers that we are going to put here and find the events, the accept events, or that reproduce the physics, the correct physics. So it's usual to use, for example, 100,000 events. But for our case, we are going to use the thousand for time. Okay. Here we can define the type, the particle type. We have one if we use proton or antiproton. Two, if we consider an ion beam or a photon emitted by the electron, or electron positron beam, or a muon anti-muon beam. If we set 0, we don't consider parton distribution function. For this example, I set 0, and we can put here, for example, the energy. We have in the first beam we have 500 GeV, the same thing to the second beam, and we have some cuts here. For example, we have here the minimum transversal momentum PT of the pairs of charged leptons. So the minimum is, for example, 10 GeV. We have another important kinematic variables. For example, eta means the pseudo rapidity, the rapidity of the leptons. So in that case, we have 2.5 GeV. That means we need to see the interpretation of the pseudo rapidity is given by the first lecture that was, I think, that by time. That is rapidity. Remember, pseudo rapidity I show in the first lecture that is given by eta. Okay, eta are related to the angle. For example, if we take in that file that eta is equal to 2.5, that means that for 2.5 that is approximately is in this region. Okay, so we only consider for the integration in that case electron positron pairs between that point and that point in the another region. Okay, that region we only consider the integration. So that means cots in or integral. So this is important because we don't have, for example, we don't have detectors in the exactly in the beam of the particles, obviously. So we don't have technology to detect the collisions at the same region of the beam. So we need to put that types of cuts. This is important. So we have here the delta R separation between two pairs of leptons and another information. So to run the calculus, we use output, we use launch, and we wait in that time appear, for example, the cross section 42 picobarns, the units that MathGraph use are picobars. This is important. So this is the manner that we can use MathGraph to generate events. And for example, we have another here. We have another commands. Generate e plus and minus, e plus and minus, and a photon. So we can display diagrams, and we have in the final state we have the electron positron here, electron positron that emits a photon. Okay, so that types obviously we have a lot of diagrams to do the calculations. So we can generate, for example, another example. We can generate with protons. Generate proton, generate electron, positron, and jets. We have here 72 diagrams. Display diagrams. So if my computer don't explode, we have here all the 72 diagrams. We have jets that are partons. We have gluons at the final state, and we have, for example, we have quarks, the different quarks of that has part of the jets, and we have a lot of diagrams. Okay. If you see, we only have at the final state partons, so that events are at parton level. So this is important. If you do, for example, the same calculation, generate proton-proton, producing electron-positron pairs and a jet, you need to install Pythia, okay? By the time of the installation is around 1 hour. So here I need to pass to my own program in that I have installed different data alternative programs here. For example, we can generate generate proton producing electron positron. And if you dot output collider school, and then you do launch of that folder, appear different things here. I can activate with the number 1 the hadronization using Pythia. So that implies that MathGraph takes each one of the final partons and combine with an internal algorithm to produce mesons and baryons at the final state. Obviously, that calculation take a lot of time. Okay, so I need to cancel that that calculus. You cancel with Control C, okay, as is usual in Linux. Another important command here is, for example, display process and display diagrams. We can generate another events, and we can combine events. For example, generate e plus and minus, e plus and minus. Okay, this is the first process, and to add another process you use add process E plus, E minus, coins E plus, I minus, and a photon, for example. So we have now 20 diagrams. In that we have the process that contains the two pairs of electron positron, and the original process that only contain electron positron. So you can combine events, okay, process with that command, and we studied that a command to import another model, and you can, for example, that command are very important. You can generate E plus, E minus, generate E plus, E minus. If you do that, you see that you have photons and Z bosons, okay? But if you that with this slash and Z, you say to MATLAB that only show diagrams that not contain the Z boson. We have only diagrams with the photon, okay? So that command means that with slash means that we reject all the diagrams that contain the Z boson. And we can generate, for example, only diagrams that are resonant at the Z boson with that command. Generate electron positron produce a Z, and Z decay into pairs of electron positron pairs. Obviously, we only have this diagram at the S channel. We have, for example, that command, for example, display generate again E plus, E minus, E plus, E minus. But here appear the Higgs boson, so we need to charge the model that contain the Higgs boson. I don't have here, but we can use the same model that I have here. Models, we are going to use that model here. So to do that, because I do that because here we have the Higgs boson, so we need to a model that contains the Higgs boson. So we initial MATLAB, and here generate E plus, E minus, generate E plus, E minus, and with that command we reject all the Z channel related to the Z that contain the Z and the Higgs boson. Display diagrams. We can see that we have, for example, in the S channel we have the photon, and the T channel we have the photon, but we don't have the S channel for the Z boson. So that comment represents that with these two symbols we talk to MATLAB reject all the diagrams that contain in the S channel that particles. Okay, we have here, we can combine that symbols, for example, generate again, generate is here, generate electron positron pairs, but we don't need diagrams with the S channel with the Z boson, and we don't need diagrams that contain the Higgs boson, the Z boson, sorry. So we only have three diagrams. We have the diagrams that contain the S channel and the T channel for the photon, and don't contain, as I put here, don't contain diagrams with the Z boson at the S channel. So only we have the T channel for the Z boson, and we don't have diagrams that contain the Higgs boson. So that we can combine that types of instructions. Did why is the motivation to exclude? Mhm. To exclude the T channel? This is a good question because I use all the manuals of MathGraph, and for now I don't find the form to exclude the T channel. Okay, so for me, I don't know what is the command to exclude the T channel for now. So if I find the answer, I send the answer for Farinaldo.
Okay. Oh, oh. First of one, you need to generate the process, and after that, the program generates cards, and you edit the cards, and in the cards you have the information about the energy,
Of,
yeah,
of the collision.
the energy of the collisions, and all. I don't know, but where do you modify the information about the luminosity of the process, for example?
Okay, this is a good question, and that question is answered at Friday
Okay.
because it's a part of the analysis.
Okay.
Because in the analysis we only analyze cross section don't depend on the luminosity.
Yeah.
Number of event depends on the luminosity. So we need to translate using that equation. That is my favorite equation. That is n equal to the efficiency times the luminosity times the cross section. In that part, we can modify the luminosity of the experiment.
Okay. But let me see. You have the information about the energy, for example, in the KE KB experiment. You have the energy of electron, the energy of the positron,
Mhm.
the luminosity of the process, and then you ask to the program to do the calculation of the sigma of the cross section that is independent of the luminosity. Okay,
It's
you say
independent.
that computer, the program, calculate the cross section with this luminosity, and the output of that request is the number of events.
Yes, this is the analysis, the final analysis. with the math graph at Python or hadronic level, we only do the calculation to find the cross section, and we know cross section is independent on the luminosity. Luminosity depends exclusively on the experiment.
Yeah.
So we need to put that equation in a program, generate all that events and multiply by the luminosity of the experiment and some efficiency and obtain the distributions. Okay. For example, here as default, media analysis use the following. I think that is the last. For example, here we are going to generate that process and show the distributions. Okay. Generate proton producing E plus E minus. Process 1. Launch process 1. And we are going to analyze with media analysis 5. Media analysis 5 is a program tab for do cuts and analysis related to the number of events. And in that program are implement some of the principal kinematic variables. So we are going to see that appear the luminosity of the experiment, but is the 10 inverse of femtobarns, I think so. So, for example, using media analysis in that case, we obtain the cross section of that process, proton producing two pairs of electron positron, and here appear the cross section in picobarns. But in the process 1, that was the name that I set for my result, I open index, that is a form to see the information of the process. As you click here and the media analysis report, you can see, for example, the invariant mass of two pairs of electron positron, and we have here the luminosity, the integral luminosity, that is 10 inverse of femtobarns. So media analysis is only a tool to analyze histograms, and for that histograms you need three things: the cross section that is obtained by MATGRAPH, you need the efficiency of the experiment, and you need the luminosity multiplied by the luminosity. MATGRAPH do that automatically. We can change the luminosity, obviously, inside of media analysis, but in my lecture of Friday, sexta, yes, of the Friday, I do that using the luminosity, for example, of the compact linear collider, that is 5 inverse of A2 bars in the case of the click experiment. So we finish here. This we can use initial distribution, initial visualization for the histograms. For example, we have here the eta, that is the pseudo rapidity that we obtained in the first lecture. We have the transversal momentum and another things that are important to the analysis. So we are going to talk a little about the Friday. Okay, so we finish here. And any question?
Anyone here has a question? Okay. Okay.
I was wondering because it's very useful for me right now. And doing, for example, I'm working with a process beyond the standard model, and I want to do one scan, for example, for a particle. In this case, is dark photon. I want to explore a range of masses. Can I do that here? And uh, it will show something like a table or something with that the cross section in comparison with the mass I'm exploring here in the.
Yes, this is the lecture of Friday. I create a script to do that.
Okay. Okay. Thank you.
Okay, we have had a question yesterday. I completely forgot to read. Someone in Google Meet asked you to comment about the constraints on the Z prime, because yesterday you comment about the Z prime, right?
Yes.
And you told that your favorite particle. And someone asked about the constraints right now about the mass and stuff like that. The
Yes.
experimental constraints.
If you have first of all, the constraints of a Z prime depend obviously on the model. Atlas experiment published a paper in that he he do a scan of the invariant mass of two pairs of leptons, of muons and electrons, and they show a distribution. Okay, and you find the constant on your model, compare the cross section, and you find that, for example, in our cases, we find in another paper, I find that, for example, the Z prime need to be has a mass of 4.6 tera electron volts if you model consider a Z prime with higher, okay? But we have another models that contain Z primes that are very, very light, okay? So we can use, for example, collisions between ions or another types of experiments that search for dark photons, for dark Z, etc. That has mass of GeV, for example, because using the LHC we don't see particles of GeV, for example. Mhm.
Okay, the other request in the Google Meet was to try to explain how to install the root.
What is the? I have a tutorial to install
The root.
Mhm.
Okay,
I can send.
the tutorial is a kind of a text, an archive or something like that.
It's a text for now.
Okay. So maybe you can send me and I will put
Mhm.
in the Google Drive for you guys. And do you have any more questions on YouTube? Can you take a look at Google Meet, please? I think you have Google Meet on your PC.
And
No, just about the root, right?
Mhm.
Okay, so we are going to finish here. Just to remember you that the lecture notes and the materials are on Google Drive, the link that we posted. The attendance list is available on YouTube as well. And this broadcast is going to finish, and we are going to open another one to the next lecture. So thank you very much for your for you being here, and we are glad that you are here. And see you in a few seconds. Bye.